Hello, welcome everyone. Welcome to the another session of OpenFlow cytometry. Today we're going to follow up on the last remote class that we had on cell sorting. So we're going to go a little bit into more depth with some of the processes to set up the sorter, and maybe go through some of the troubleshootings that we typically do in cell sorting. I just want to remind you, this is a joint effort between the Crick Institute and Memorial Sloan Kettering. We have been doing this for quite some time. Just to let you know that you can use the Q&A to ask questions if you need. We will be happy to interrupt the session to answer your questions as much as possible. If we see that these questions can be answered at the end, we'll also leave some time, hopefully at the end, to answer the questions. But feel free to use the Q&A to ask these questions. I'd just like to introduce myself. My name is Rui Gardner. I'm the head of the flow cytometry core facility at Memorial Sloan Kettering. And I just want to say that today is a special day where Kathy, that will introduce herself, it's her last day here at Memorial Sloan Kettering. The great news is that this will become a partnership of Memorial Sloan Kettering, the Francis Crick Institute, and the Whitehead Institute at MIT in Boston. So we won't get rid of Kathy for sure. She will continue being involved in these remote classes. So we'll continue to have the amazing pleasure of having Kathy here giving these classes. So I'll give it back to you, Derek.
Actually, maybe Kathy, you should go first.
Oh yeah, Kathy. Yeah, sorry.
Sure. Thank you, Derek, and thank you so much, Rui, for a kind introduction. So yes, my name is Kathy Daniels, and I work for one more day, or about 4 more hours, with Rui here at the Memorial Sloan Kettering Cancer Center in New York City. So I've been involved in flow for about 8 years now, and I'm so grateful to have had this opportunity with Rui and Derek, and continue on as I head up north to the Whitehead Institute in Cambridge. So really looking forward to continue on with this, especially with cell sorting today. On to Derek.
Okay, thanks, Kathy, and glad to hear that we're going to be able to continue to do this. So my name's Derek Davis. I am the Science Technology Platform training lead here at the Francis Crick Institute in London. And what we're trying to do, of course, with these OpenFlow webinars is to not only give you the theory of some of the areas of flow cytometry, but also the practice as well. So, as Rui said, we're following on what we did last time. And last time, a month ago, we were looking at cell sorting using a relatively user-friendly walk-up cell sorter, the Sony SH800. And today, we're going to move on to the BD FACSAria 2, which again is possibly a familiar machine to many of you. So we're going to recap a little bit about the principles of cell sorting. If you remember from last time, one of the crucial things about cell sorting is setting the drop charge delay, and I'll come back again to that in a moment. We're going to see how we do that in the BD machine. We're going to have to think about how we can adjust the way we sort to capture the cells that we're interested in. And as usual, we're going to do some practical. We're going to perform and check a relatively simple sort. It's only going to be 2 colors, but this time it will be cells rather than beads. So, slide from last time, just to show you what the pros and slight cons are of electrostatic drop sorting, which is the way that we do it in flow cytometry. An electrostatic drop deflection is the same way that inkjet printers work. And in fact, the inventor of the inkjet printer, a guy called Dick Sweet, was involved in the early days of flow cytometry, and we'll come back to him a little bit later on. But the great positive sides for us are that we can use electrostatic drop deflection sorting to isolate a population of interest, and that, of course, is what many people want to do. They'll do a transfection and they'll want to retrieve their 10% GFP positive cells, or they'll want to separate the CD3, CD4 positive cells in blood. And the reasons why they might want to do that are varied, and sometimes we don't necessarily need to know too much about that, although it is very useful to know what the end product is going to be of our cell sort. But we can sort cells to a high degree of purity. 98, 99% purity should be fairly routine, and that of course is what people initially want. But we can also sort on as many parameters as we can measure on our flow cytometer. So if we have an 18 color cell sorter, we can do an 18 color experiment and sort some populations from that. And we can sort those populations on the basis not just of the presence of the marker, but also the level of the marker. So going back to the GFP example, if we wanted to sort our bright from our moderate, from our dim, from our negative GFP cells, we could, because most of our flow cytometers, in fact, nearly all of them, will allow us to retrieve more than one population at once. In fact, the majority will do 4 populations simultaneously. There are a few that will do 6 populations at once. And one of the growth industries in cell sorting, certainly what we've seen at the Crick in recent years, has been single cell sorting. And that goes hand in hand, of course, with the rise of single cell genomics. So we do a lot more of that into 96 or 384 well plates. There are a few slight downsides, I suppose, of cell sorting. It's more expensive. The hardware itself is more expensive than an analytical flow cytometer. It does require a little bit more expertise, but that doesn't mean to say that you can't be trained to run a cell sorter. Both at MSK and at the Crick, we do train people to run their own cell sorts. Sometimes, though, it can be trickier to get time on the machine. They're not as prevalent as analyzers, so you may have to plan a little bit further in advance when you're thinking about cell sorting. And there is a time limitation. If you're just sorting a few 100,000 cells to regrow, that's going to be relatively quick in most cases. If you're sorting large numbers of cells of a relatively rare population, you may spend a long time, maybe even all day, sorting cells. But here's a slide again that we showed last month, the all-in-one cell sorting in one slide. So if we think about what we're doing, in our cell sorter, we're doing very much the same that we're doing in an analyzer. We're hydrodynamically focusing cells so that they flow one by one through a flow cell past one or more lasers. So a cell is going to come in here and it's going to pass through multiple lasers. Now in the FACSAria that we're using today, the laser beams pass through a cuvette system, and that has some advantages, slightly more sensitive. But what we then do is we eject our column of fluid into air through a nozzle, and that nozzle can be of varying sizes, and the size that we use will vary depending on the cell type we're using. But once we eject that column of fluid into air, we want to make it break up into droplets, and we do that in a very controlled way. We vibrate this nozzle very quickly, maybe up to 70,000 times per second or more. And what that does is it creates a standing wave of vibration in this column so that our drops start to form at a particular point. And this is what's going to enable us to actually sort our cells. We're actually sorting drops. The cells are just going along for the ride. But we'll see that in a little bit more detail in a second. So as our cells pass through our laser beam, that's the point at which we understand what markers they're expressing, what their phenotype is. What we're doing in our cell sorters is we wait for the cell to pass from that interrogation point till just it's at the end of that column, so it's in the last attached droplet. And at that point, we charge the stream. So we're using an ionized fluid, we're charging the whole of that stream, and we keep that charge on for the time it takes to form a droplet. Now, the cytometer knows that because it knows the frequency at which it's making drops, so it knows how many microseconds to apply that charge for. So what that means is that as that drop containing our cell of interest, as that's breaking off, that drop is now going to contain a charge, or it's going to have a charge on its surface. Okay, it's a bit like a Faraday cage. It's not going to affect the cell that's inside that drop. It's the surface that's charged. And at that point, once that drop has just broken off, we then discharge the stream. So the stream now is back to neutral, but our drop containing our cell still contains that charge. And now we pass it through an electrical field formed by these two high voltage deflection plates, and then it's going to be dragged off one way or the other, depending on its charge, into a waiting receptacle, which can be a tube, it can be a plate, it could be a slide, it could be almost anything. And you'll see a bit of this later on, and you saw that last time. This is the picture that we see, and one of the skills, if you like, of being a cell sorter is that you get to recognize that this looks like a good image. We can see our solid column here starting to break up into droplets, but they're still attached. Here's our break off point, and then here are our detached droplets. So as with any flow cytometric experiment, the first thing we're going to do is make sure we're happy with the performance of the sorter. So we've actually already done that, but Kathy will maybe briefly mention that when we go to the ARIA in a second. But the important thing in the cell sort is to set that drop charge delay, the time it takes our cells to go through the interrogation point until they come to this last attached droplet, the break-off point. To do that, as in many things in cytometry, we're going to use beads, because working out how long it takes a cell, or a bead in this case, to pass from the interrogation point to the break-off point tells us how long we have to wait to apply that charge. Now, it's quite difficult for us to show you the machine in action. We'll be looking a lot at Diva. So here's a picture of what the ARIA actually looks like. So here we have the camera that actually takes the picture that we see those drops. And here's our flow cell, a quartz flow cell. So our cells are being hydrodynamically focused, so they're flowing one by one through this flow cell, and this is where the lasers are going to come and intercept with those cells. So we capture the fluorescence that's emitted and the light scatter. The cells then pass through a nozzle in this system. So this is a picture of an ARIA nozzle. The actual orifice is just inside there where that O-ring is. And then a stream will be ejected into air, and it will pass through those deflection plates. And if it's not charged, everything is going to go into this waste catcher. But these deflection plates are the things that are going to allow us to pull our cell off one way or the other, depending on its charge. And in this system, we also have another laser here, the so-called Accudrop laser. And this is going to be used to illuminate the stream and the side streams. And that's what's going to help us to determine the drop delay, which we'll see in practice in a second. But here's the Accudrop laser in action. We've overridden the interlock here, so you can see the red laser hitting the stream. So here's another picture that we quite often show. So here's our stream of drops, charged droplets. And because they're charged, when they pass through the high voltage deflection plates, they're being dragged away from the center stream. The center stream is going into the waste, but our drops containing our cells of interest are being deflected and passing through to our tube. And this is another image that we'll be looking at in a moment. We will be making sure that we can see our center stream, and the ARIA is capable of looking at 4 different populations at once. So we can sort 2 populations to the right, 2 populations to the left. And we're using that laser, that Accudrop laser I showed you just now, to illuminate those side streams. So what Kathy is going to show us in a second is how we set that drop charge delay. So just to give you an idea before we get there, if all our cells are not being sorted, they're all going to go to waste. So we'll see all our cells in the waste stream. What we're going to do is we're going to alter the drop delay until some of our cells are being deflected. And we'll keep altering it until actually all of our beads are being deflected. And we know that we've set the correct drop delay when all of our beads are being deflected to the left and none of them are left in the waste stream. So that's a little overview of what we're now going to see in practice. So I'm going to hand over to Kathy at this point on the actual machine, and we're going to actually look at that setup.
Thank you so much, Derek, for that awesome introduction. So I'm going to go ahead and I'm going to start sharing my screen here. And do we all see the Diva software now? Showing up? Okay, perfect. All right. So as everyone will be kind of familiar with from some of our previous sessions, when we log into Diva, we have multiple windows that come up. Okay, now this is our first session looking at a FACSAria. So this Diva software is a little bit different in the sense that we see two more windows that we typically wouldn't see right now. So what we essentially see that we hadn't seen in prior OpenFlow sessions is the side stream window, which is where I'm kind of moving the window right now. And Derek had shown some of these images in his slides. And we also see the break off window right here. And that's where we see the nice formation of droplets as the sheet is going through the instrument. Okay. So as Derek mentioned, it's very important that we make sure that we QC our instruments, right? So what we do every day is we make sure that the optical alignment of the instrument and the performance of the instrument is as expected. So that is something that we have carried out and done today. So we're not going to review that at this point, but it's important to know that that optical configuration is optimized for the performance of the instrument. Okay. General overview for anyone who might not have been at our prior sessions. There are multiple windows that are here in Diva. So we have the browser window, and that's where you're going to see your account name. And you're also going to see any experiments that you have. They can be in a folder or they can be separate of a folder, right? So we can see we have some experiments set up here, including our QC, which we had run earlier in the day. Then you also have a cytometer and an inspector window, which are currently blank, but we're going to see those capabilities once we create an experiment. And you have an acquisition dashboard, which will allow for us to actually run sample. Again, I went over this, this stream window over here. Worksheet is where we're going to be able to see all of our data. Okay. So with that being said, let's go ahead and get started with our setup of the sorter. So when we first come in, what's going to be very important is to make sure that our droplet formation is as we expect it to be. So today we're working with the 70 micron nozzle on the FACSAria. That's the high pressure sorter option that we have here. So it goes to 60 PSI and the size of the nozzle is 70 micron. And what we can see when we're looking at this window right here is that we have the droplet formation. And we have this gray bar right here, which is the gap. And that gap is going to be the difference between the top of the image, or sorry, that gap is showing the difference between the last attached drop and this first attached drop and the satellite drop right here. So that's the gap that we see. And then we also see a drop one. That is this thin gray line right here. And that's the difference between the top of the image and the center of this detached drop right here, okay? These are things that are going to be very important to us as we go ahead and start setting up for our experiment today. What winds up happening with 70 micron nozzle is, and with any size nozzle as we're starting to sort on the ARIA, is we have to take into account the pressure of the instrument and the pressure that's applied to the sheath tank. And then we also need to make sure that the frequency that's applied is correct, in addition to the amplitude, so that we get the optimal droplet formation. So with the 70 micron nozzle, what winds up happening is we can generate more droplets per second in order to go faster since we're at a higher pressure. With the 70 micron nozzle, we typically run at about 88,000 hertz or 88 kilohertz, right? That means at this point, right now, we're generating 88,900 droplets every second at the instrument. The amplitude is what we can apply, or what's applied to be able to adjust where this drop one position is at the instrument, or on the droplet camera, right? So when I first come in, what I'm looking to check at the instrument itself is to make sure that this droplet formation looks as expected. So what I want to see is I want to see this nice last attached drop with a gap that's within the normal range for the nozzle that we're working with. And I also want to make sure that these satellite drops, which you're seeing right here, I'm clicking, which is why those options are popping up. But we want to make sure that these satellite drops are reattaching to the main drops. And the manual from the BD FACSAria instrument manual tells us that it wants us to have those satellite drops reattached within about 6 droplets. So what we see here is this formation of the droplets is looking very nice. And just to show you what happens if we adjust the amplitude, I'm going to change this value right here so we can see real time what happens if we do make that adjustment. Okay, so if I go ahead and I start making changes to the amplitude, what we see is this gray bar right here is starting to get a little bit wider. And what we also see in this window is that the gap value is now at 10. So right here in this text box is where I can tell the software, this is what I want the gap to be if I'm at my happiest, right? Like if the stream is, or if the droplets are looking exactly how I want them to be, I want that gap to be at about 7. If I increase this amplitude, the real value of the gap is going a little bit higher. So you can see it's at 11. I go up to 6.6. This gap is widening, and we see it reflected here because that is the real readout, okay? So what I'm going to aim for after our initial characterization is to get this gap to match up, and I can do that either manually by adjusting this amplitude, or what I can do is I can turn this sweet spot on in the software. And what's going to happen when I turn the sweet spot on is it's going to automatically modify this amplitude to try and get it as close as possible to these values that we've put in. What we typically recommend to our researchers who utilize the ARIAs for self-sorting training in the facility is to never change the frequency, because we typically have that set up in the core facility to a point that's optimized for the nozzles that you're working with. So what we say is to make minor modifications to the amplitude to get these values right here and right here for the drop one and gap to be as close as possible to our predefined values, right? So if I'm coming in and I see that this value for drop one is way off, right? That was because I just made this change to the amplitude and I went down one whole value, okay? See, what happens on the ARIA, which is nice, if I hit the control key and I hit any arrow, it makes changes of one whole integer. So if I were to come in and I were to see this, I have 2 options, because I see that I want the drop one to be at about 211, and the real value is reading at 157. My gap is okay, but my drop one is not where I want it to be. So my 2 options that I have are either to turn on sweet spot, and that sweet spot is going to try and, again, get it to these predefined values that I have in. And what you can see is as I hit that sweet spot, it adjusts this amplitude automatically in the software to get as close as possible. And it did it fairly quickly. Now, I tend to be a little impatient, so because I've been working at the cytometer for so long, what I'll default to do is to make minor tweaks to this amplitude to get it as close as possible, and then I'll turn the sweet spot on. because then what's going to happen is the software is going to monitor to make sure that those droplets look as they should and give you a warning or pause the sort if there are any issues with stability of the stream. Okay. Once I get started for the day, and once I make sure that this droplet formation looks as expected, what I then do is I make an adjustment to that drop 1 position, and I type in the value that's our starting point. What's important to remember here when we're at the sorters is that any slight changes to temperature or humidity can actually make minor adjustments to where that drop 1 position will fall day to day. So a value that's different by 100 is a larger change. A value that's different by about 10 or 11 is not so dramatic. And that's where I would go ahead and make this minor modification to update that value, and then keep an eye on that number as the sort is progressing and as our setup is progressing throughout the day. Okay. So that's what I would do to go ahead and get started when we first sign into Diva and go ahead to get started with our setup for the sort. What I want to make sure that everyone is aware of as well is that if you see that these satellite drops are not recombining at all, or if you see that it takes a very long time for them to recombine, you might have some issues with the sheath. You might have some issues with the nozzle itself. You know, there could be a couple of different reasons, and I highly suggest that you go ahead and you refer to the ARIA manual, or if you have specialized technicians or cytometrists in the facility, to reach out to them. Okay. So.
Kathy, sorry, let me just interrupt because there are a few questions here. So somebody was asking a question about the nozzle and pressure, and this is an important question. We actually addressed it last time, but it's important for everybody to be on the same page. So Simon was asking if the size of the nozzle and the pressure has an effect on the stresses put on the cell and subsequent downstream viability or transcriptional profile.
So that's definitely a great question. I think that's a heavy question because there's a couple of different things that we can talk about there, right? Mm-hmm. So the size of the nozzle and the pressure absolutely can have an impact downstream for the cells. So what you want to consider is the size of the cells and the size of the particles you're looking to be working with, right? So that you can keep that in mind. So for when we're going to be doing our sort today, we're going to be sorting lymphocytes. So we've chosen to go with the 70 micron nozzle. Also, what you want to keep in mind is if you are working with lymphs, maybe you're working with activated T cells or something like that, they might be more sensitive to being at higher pressure, and it might warrant you going to the 100 micron nozzle and going down to 20 psi. Okay, and this is just the ARIA, so you might be working with a 100 micron nozzle on another instrument that's at a different pressure. These are usually things that you can modify yourself as well. Now, downstream transcriptional, that's actually something that is a hot topic, and it's something that we want to explore here in our facility. I don't think at this time there's been enough research to actually say whether or not there are downstream impacts. I think there's been a lot of questions out there, and there are a lot of people working on it. I know Peter Lopez is working on the 6 project, and there's a lot going on, but I don't have an answer for that right now.
I would actually add to that it's not so much that we don't know if there's an impact. I mean, definitely there are impacts in some cells that are more sensitive to these changes, but due to pressure. The thing is, a lot of these changes actually have nothing to do with the sorter. They come actually during sample prep. So there hasn't been a lot of people comparing the sample before it's sorted and the non-sorted sample, but there are some cells that definitely there is a change. The problem here is that nobody knows exactly what kind of changes those are, right? And is it really impacting anything? So that's the difficult part to address, right? And there are a few people addressing this. But nothing conclusive has come about that.
Yeah, I mean, I would say that flow cytometry really, certainly the initial sorting experiments are all done on T cells, aren't they? And T cells are very robust.
Right.
I think there are some cells that are more susceptible, but as Rui says, it's sometimes difficult to pin down where that susceptibility has happened. So we do try and make sure that we get ourselves through the sorter as quickly as possible, so that we try and minimize any issues that we might have with that. And as we've seen, we can change the size of our nozzle. We can change the pressure. We don't have to run a 100 micron nozzle at 30 psi. We can drop that if we think that's having an effect on the cells. So we have some flexibility there.
Right, right. Very important. So another question here is that, so somebody, this is anonymous, somebody said, in our facility, we adjust phase value to adjust the drop one value. Is there an impact when the phase value is set to 0? So I'm not sure here if they're talking about an ARIA where you don't adjust the phase, you adjust the amplitude, or if they're talking about another instrument. And so depending on the instrument, I actually have no idea if, setting the value at 0 would be something problematic or not. I'm thinking of the MoFlow, for instance, where we would set the phase at any from 0 to 360 degrees, and it doesn't really matter what the value is as long as you have a good stable drop break off, and it deflects the drops properly, right? Oh, it's an RS3. It's an RS3 they're mentioning. So yeah, I mean, we don't adjust the phase here in the ARIA. I don't know. Did you mention that, Kathy?
No, I was just going to bring up on the from what I remember on the Astros at least, and and that instrument with the MoFlow is we would adjust the charge phase based on the fanning and kind of try and go in the middle of the 2 points where the fanning was the worst and kind of set it in the center of that and subtract by 180. So that's what we would do on that instrument.
Mm-hmm. Right. So I don't know if they were talking about the amplitude. So the amplitude, you can't set it to 0, right? It goes down to 1, I believe. That's the lowest amplitude we can apply. I mean, right. There's always, you have to apply an amplitude. So I don't know if that was the question, but definitely, yeah. In other instruments, you can adjust the phase, right? So another question from Svetlana. This is more specific to core facilities, not so much about sorting, where she's asking if we actually start up the self-operated BD FACSarias. Is it the core staff or the researcher? In our case, in the morning we do the startups, but that's a logistical question. We have staff to be able to set all these instruments up. But outside of working hours or on weekends, all of our self-operators know how to do the startup and shutdown, so they start up the instruments themselves. I don't know how.
I would completely agree. I would completely agree with that, Roo. We train everybody how to do it so they can do it. But normally during working hours, we would start that up. And sometimes even after working hours, if they're tied up, they'll ask us to start it up for them, which is fine. But they can do it, especially if they show up at a weekend.
Mm-hmm. So here's another interesting question. What do the gap and drop one numbers represent? Are they pixels? Yes, they are. They're just relative.
That's an easy one.
Exactly. The drop one is the distance between that line there, that thin line, to the top of the camera in pixels. Exactly. So it's just the distance. Yeah. So actually, if you move the camera, those values will move, but the drop break off is actually in the same position. So that's something to look out for. Don't knock the camera while it's sorting.
Yeah. We won't do that now.
Exactly.
Yes, I could do it for educational purposes, but it might kind of knock it out. So I won't do that for today. Maybe I'll wait till the end. And yeah, here that thin line that Rui is talking about. Now that I put the spotlight on, you can see it a little bit better because I was trying to click before and it changes some of the options on that window. And it's important to note, I think, as well here, and this is something I didn't say just yet, but up here at the very top of this break-off point window, you do see the size of the nozzle, and that's written into configuration. So it will tell you when you're turning on what size nozzle you're working with, and that's controlled through the instrument configuration. So we're giving you an overview today of how to do the setup, and it's not considered a full training, right? Because there's so much more that's involved in this when we're talking about the fluidics. So you can see right behind me, there's another ARIA We have the waste and the ethanol and the sheath. It is very involved, and this is partly kind of going back to a little bit of Svetlana's logistical question. When we train people, it's 5 hands-on sessions of at least 2.5 to 3 hours, right? And that's just for our facility. Some facilities do even more than that. So we're giving you the overview today, but there's a lot more involved in the sorting. So we're just giving you the practical considerations. Okay. So with that being said, and now that I have this spotlight here on my mouse, which I think will be very helpful, what we're gonna, I think I just got rid of it, so let me put that back on. Okay, so after I come in and I make sure that these droplets all look as expected, the next thing I'm gonna do after we did the optical configuration, which we did a little bit earlier, that we're not gonna go over today, is we're gonna make sure that our setup is correct in order for us to have the appropriate drop charge delay that Derek was talking about in some of his slides, okay? So what we actually have set up in our facility is we have an experiment that we have in our browser that's specifically for calculating the drop charge delay. So what I'm gonna do is I'm gonna open up this Accudrop experiment, and a quick refresher for anyone who hasn't seen the Diva software just yet or hasn't been to using Diva in quite some time. When you see this experiment book is closed, even though you can expand out on it and see that there are tubes associated and there's information here, we're not really able to see much, and that's because we need to double click to actually open the experiment. Once we open that experiment up, what you will see is that we do have a worksheet and we are able to see our data, okay? Now, move this so that we can make sure everyone sees everything, so the Zoom window blocking the way. What I'm gonna do first when I open up this Accudrop experiment is I wanna make sure that when we go ahead and we go to test the drop charge delay with the Accudrop beads, I want to make sure that I'm actually going to be able to see those Accudrop beads as they're being deflected and as they're being sorted so that we can appropriately calculate the drop charge delay. So when we look at the side stream window right here, that's where I'm going to go to next, okay? In this side stream window, we have the options to turn on the high voltage deflection plates. We have the option to do a test sort. There are also other options in here, optical filter, attenuation, waste drawer. We'll go over this in a little bit. But what I'm first going to focus on now is making sure that that Accudrop diode laser that Derek had mentioned in the slides that we brought up is accurately aligned so that we can capture and visualize all of the streams as they're being deflected, okay? So if we're looking at this window right here, what I'm going to do first is I'm going to turn on the voltage. Okay. You can see that did nothing. You say, Kathy, all right, great, you turn on the voltage. Big ta-da, what did it do? Nothing. Because right now I don't have any test sort that I'm carrying out. So if I go ahead and I click on test sort right here, what do we see right now? In addition to the center stream, we also see this population to the left and this population to the right, okay? This is the far right stream and the left stream that have deflection percentages associated with them. What we do in order to make sure that our Accudrop laser diode is aligned correctly to the specific, or to the stream and the deflection, or to the streams as they're being deflected, the droplets as they're being deflected, we make sure that we adjust the values for the far right, the left, the right, and then the far right, so that we're visualizing all 4 deflection points. Now what I can do, I can go ahead and you can see I'm kind of coming over to the side here and it's going to be out of your line of vision. But if I start adjusting the Accudrop diode laser, which is a red laser, I'm losing this left, or these droplets are being deflected to the left, okay? as I rotate that Accudrop diode laser alignment the other direction, I'm starting to lose the visualization of those deflection streams on the right, okay? So if I go ahead and I go back the opposite direction, my aim is to get these as bright as possible and as in focus as possible, right? So there's actually a focusing, it's a little bit further behind, so I'm not gonna go into too much detail on that, but I want these as nice and bright as possible. And again, it's very important to make sure that all of those 4 points are able to be visualized, okay? So now that I have all 4 of those that are showing up nice and bright, what I'm then gonna focus on is this center waste stream, okay? What winds up happening is that we have this second, third, and fourth drop, which is applied to correct for any fanning that there might be in the center stream as a result of these other droplets that are being deflected, okay? So if I come in and I adjust this value and I start bringing it down, you're starting to see this fanning of the center stream. That's not going to be ideal. We want that to be nice and tight. And this is something that you have control over in the software. And it should not change very much from day to day, but it's important that you have the control to correct for that, to make sure that we're minimizing that fanning of the center stream. So what I'm going to do is I'm going to come up, and as I start adjusting this second droplet percentage correction, you see that it gets nice and tight there. As I start going too far up, what do we see? We see the same thing is happening if I go too far up in the second drop. Typically, what we wind up suggesting to our users is to go in the middle of the 2 points, right, where it starts to kind of come out. So this value of 18 or 19 works just perfectly. The third and the fourth drop correction have a little bit of a lesser impact on the center waste stream, and we typically don't need to adjust those values so much as we do have to adjust that second drop. Once I make sure that Accudrop diode laser is aligned as we expect it to be, and once I make sure that the center stream is nice and tight, what I can do then is I can go ahead and change these deflections to 0, because all that I'm going to have to worry about as we get started checking our drop charge delay is this left stream, okay? But now that I know that everything is set up appropriately, what I'm going to do is I'm going to turn off the test sort rather, and I'm going to turn off the voltage. Now you can see we already have this experiment set up, which is why I was able to open it up. And what I'm going to do is I'm going to highlight this tube that we have set up in the browser. And I want to take my Accudrop beads and give them a nice vortex. So Accudrop beads are beads that are produced by BD, and they have an excitation at 670 nanometers, and they emit light around 750 nanometers. And we can use that with the optical filter in order to be able to see when the droplets are being deflected. So I'm getting a little ahead of myself. Let me go ahead and load these beads that I just put onto the sample chamber. And in the acquisition dashboard, I'm going to select load. Okay. You see that we have a forward and side scatter pot set up. And there's a P1 gate that's right up here in this top left corner. It's a unique gate, not one that you would expect to see for cells or beads or anything like that. And then we also have a not P1 gate. So that's called an inverted gate. And we have this set up already in advance in the software in our experiment. But if you need to do this yourself, you just right click on a gate from the population window, hierarchy window, and you would be able to invert the gate. It's currently already inverted, which is why we don't have that option. So we can see that we have our Accudrop beads showing up here. And what I'm going to do is I'm going to look at this threshold rate, because I want this going closer to about 2,000 to 3,000 events per second. So from the flow rate, what I'm going to do is I'm going to change this value, And again, this is different from what we see on the Fortessa, the LSR2 instruments, where we control the pressure differential on the instrument itself. Here it's controlled through the software. Then what I'm going to do is I'm going to expand out on the global worksheet. And what you see is we already have a sort layout set up in order for us to be able to calculate drop charge delay. Okay, I'm going to show you how to do it from scratch. So all we have to do is go ahead and open up a new sort layout here in the browser. And what we can do is we can make sure our device is in T2 mode, okay? And we can change our precision. And what we want to do first, and Derek's going to get into a little bit more detail here a little bit later on, but for the purposes of right now, we're just going to change our precision to initial. And that's going to have to do with the sort decisions and how we tell the instrument we want the droplets to be sorted. And what I'm going to do is I'm going to tell the instrument that from the left, I want to sort anything that's not P1, okay? So then what I'm going to do is I'm going to go ahead, fine tune this flow rate a little bit, and I'm going to select sort, and it's going to tell me that it's going to turn, or it's going to bring the aspirator drawer back, and it's going to go ahead and turn the deflection plates on. What I'm going to do, because I don't need these beads actually to be sorted, is I'm going to cancel this. And you can see it's sorting, okay? But we're not seeing anything in this this window right here. What I can do is I can manually turn on the voltage. And when we do that, what we see here to the left are the Accudrop beads being deflected. But what I don't have right now is I don't have any information on whether or not this drop charge delay is correct. So what I'm going to do is I'm going to turn on the optical filter at this point. And now we see a digitized image, and what's happening is it's capturing the actual, the Accudrop beads that are being deflected because it's excited off the red laser and it emits at a certain wavelength. Now what I can do is I can adjust this value here, and I can center right here where we have the Accudrop beads showing up, okay? Now, what's really important is to make sure that as we're doing this, we start off in this initial precision if we're doing the manual drop charge delay. And we want to make sure that this value is as close as possible to 100, okay? Or ideally, it should be at 100. From there, what we can do once we get this value as close as possible is we can change the precision so that we can really fine tune on where we want the drop charge delay to be. I would just like to briefly show you what happens if it's incredibly off. So I'm going to change this drop charge delay value to be 42. If I change that value to 42, we see that everything's winding up in this center stream right here. Okay, that's not what we want. So when we're in initial, we can make sure that we're getting as close as possible to where we expect the drop charge delay to be. And you can see as I'm getting closer to my expected point, this value is coming up to the left, okay? If I start going a little bit further up, you can see now we're pretty much at 100, okay? At that point, what I'm going to do is I'm going to take my precision, I'm going to change the sort decision that I'm telling the instrument I want, and I'm going to go to fine tune. Once I do that, now we're changing our sort decisions, and you can see that this is not looking as good as I'd expected to, because we want to get this value to the left to be as close as possible to 100, and we want all of our Accudrop beads being showing up in this optical filter to the left. Okay. Now, what I like to do at this point is I like to go ahead and go up one whole value. And as I go up one whole value, what we're seeing is we're seeing that there's this number here that's a little bit high, right? 8.7, 9.7. So what we're seeing is we're still seeing that there are some Accudrop beads coming into the left here in this window. So what I try and do is I try and go up a little bit higher with a in smaller increments. And as I do that, I see a lot less showing up in this optical filter to the left. It's important to note as we're going along that these two values should always add up to 100. If these values do not add up to 100, what's happening is either your Accudrop beads are old, and you need to make them fresh, or that Accudrop diode laser needs to be realigned. So now I'm going to go back down one whole value, and I did want to take the time to show this animation in Paint to show you exactly what's going on. But that is probably not going to, we're probably not going to have the time for that today. And you can see I'm getting a little bit closer, but let me go down one whole value, 43.45, and see where that is showing up right here. Sorry, so we're at about 0.2, 0.3, right? And if I go up to 45.45, a little bit high, so let me increase this value a little bit. And I'm trying to bring this value as close as possible to 0 on both sides. So what I'm checking is a drop above and a drop below, and then checking the drop delay that's in the middle of, that as we expect it to be, and trying to get that as close as possible to 100. And there will be some minor oscillations, but what we expect to see is we expect to see that value as close as possible to 100, okay? So I think at this point, I'm running slightly over on time. So what I'd like to do at this point,
Yeah, Kathy, sorry, we have a few questions that came out.
Sure.
So one of the questions, and here I don't know exactly what they mean with acoustically, but I think I understand the question. The question was acoustically not understood. What is the excitation and emission from the beads?
I think it may mean they just didn't hear what Kathy said. Right?
Oh, okay.
Oh, yeah. Oh, acoustic.
Right.
Yeah. So I do have a little bit of background here, and I apologize for that.
Okay.
Those Accudrop beads, they are excited by 670 nanometers in wavelength of light, and then they emit around 750 nanometers.
Right. So they're being excited by that red diode that's shining on that camera there on the stream.
Yes.
Yes.
Yeah. So what we see in that window at the moment is just reflected light.
Right.
When we actually put the beads on, we put an optical filter in front of the camera. So we're only letting light above 700 through or something like that, which is going to be the emission of the beads.
Right, the fluorescence of the beads, exactly. And then another question, what was the purpose of the inverted gate? That's just to capture everything. So we put a gate in the corner and then tell it, okay, capture everything, absolutely, because we want to make sure we're capturing all of the beads. If not, if we were, for instance, gating out the doublets, we would still see the fluorescence of the doublets going in the center stream, right? And so it would confuse here the actual, place of the right timing. So it's important to sort everything, absolutely everything, so we make sure that all of the beads are being deflected, and we can tell what the correct timing is.
Yeah, it's a convenient way of doing that, isn't it? Rather than setting a convoluted polygon around everything.
Right, exactly.
It's just a quick way of removing everything you want, or putting everything you do want to see.
Right. Another question is, do we need to change the window extension to 0 during this fine tuning? So without going into details, the window extension has to do with the detection part. So no, with these beads, we're really comfortable detecting them. Again, we would need only one laser to detect them anyway, with the blue laser. So as long as we're detecting them with forward scatter, that's fine. The timing will be from the blue laser to the break-off point. So we don't really need to play around with the window extension. It doesn't give it better, a better measurement of that timing, right? Okay, so we have a lot of questions coming up, and I'll let some of you guys answer these. Do you always set the drop charge delay manually?
Yeah. So what we typically tend to do is we always set it manually so that we can see if there are any minor issues or anything like that. There is an automatic delay that takes a bit longer, and that is something that you can do, but we like to train people to do it manually. And I did bring up this little image so that you can get a deeper understanding of what's going on. So this is my beautiful art that everyone gets to see. But what we're seeing right now is that we have this drop charge delay that's 44.57. And our aim is to get that as close as possible to 100 for what's showing up in that optical filter to the left based on the emission of those beads, right? And then we're checking one value above and one value below, and we want to get as close as possible to 0 here. So if I were to go ahead and I would try about 44.7 or something like that, I would see a value that's showing up in the left. That's probably somewhere around, 70 or something like that. And what you can do is you can use that to your advantage to start making minor adjustments to that drop charge delay. So I'm not sure if that that helps, but essentially this is what's happening as it's doing its auto delay, and it's calculating all of that for you. And if you get the deeper understanding of what's going on, you could make quicker changes and be able to calculate that drop charge delay yourself. So we do manual, but you can do automatic.
Yeah, so there's a couple of questions there about that. Is one better than the other? And it's the same with lots of these things, isn't it? We would show people how to do it manually, because that really is the way that the automatic way is doing it as well. I quite often do it manually rather than using the automated one as well. I find I'm quicker.
Yeah, so I would add to that exactly. So if you know what you're doing, it's as quick to do it manually than it is automatically. But the advantage of doing it manually is that you are better at recognizing if there's a problem or not. So let's say, like Kathy was saying, if the camera's slightly unfocused, or if the laser is not really shining correctly, and so you're not getting all of the fluorescence of the beads, the auto delay will calculate something for you. It won't say, oh, this is not very well calibrated. It would be nice if it did, but it doesn't do it. So you risk doing it when you do it automatically, you risk it calculating the wrong drop charge delay if all these things are not well calibrated. And that's something that you will spot quickly, like Kathy was saying. If it doesn't sum to 100% or these kind of things, you will immediately detect that and know that whatever measurement comes out is not the correct one. So that's why we find doing it manually is much better. As long as you know what you're doing, we find it better. There was another question here. So in order to set up the drop charge delay, you ideally always want to do it from your earliest first laser as reference. Not really. I mean, it does it from the blue laser, regardless of, regardless of how you're detecting it. It's always going to be the time from the blue laser, so from the trigger. Actually, I should say the trigger, right? If you change the trigger to another laser, it would be from another laser. So it's from whatever laser you're using to trigger. In this case, we're using forward scatter. So the timing would be from the forward scatter to the break-off point. If you change later in your experiment the trigger, the instrument will automatically adjust that based on the laser delay. But you want to make sure that you just measure the Accudrop correctly, regardless of the laser that you're using to trigger. I don't know if you guys have anything to add to that.
No, I would agree with that. It's from the trigger laser, so and the other lasers, the signals from the other lasers are married up in the electronics, so it doesn't really matter where they've been measured, whether it was before or after the trigger laser.
Mm-hmm. Good. Okay, that's it.
So that's
Thank you.
it for questions? Okay.
Yes.
Okay, so I think now that, apologies, Derek, I ran a little bit late, but I will pass back to you.
Yep, because we want to try and do a sort, don't we? So I'll be quite quick as well in this bit. Which obviously helps if you are ready. If I were ready with this, doesn't it? There we go. So that's what we did. Okay, so when we're thinking about sorting, what do we want? Normally, what people first think about when they come to the cytometer is they want to get a pure population of the cells that they're interested in. So they're interested in the purity of their sort. But actually, when you think about it, there's something else that you're interested in as well. Oops, sorry, and that's the yields that you're going to get. If I go back to that example I mentioned earlier, if I've got 10% GFP positive cells and I've got 10 million cells, I should get 1 million green cells. Okay? But I won't get those because sometimes there's going to be a target cell, i.e. a GFP positive cell, in the same physical drop as a non-target cell. So if I want to maximize my purity, I'm not going to sort that drop. And I also want to do this as quickly as possible because I want to, one, spend less money because I'm not on the machine for so long. But as we were just saying, I try and minimize the time on the sorter if I can, because it minimizes potential stresses on the cells. Unfortunately, you can't sort all your cells with the maximum purity in the shortest period of time. It's all a balance between these things. So we have to think about what we want. And we touched on this in our last session. So normally, this is what we're interested in, purity. In our sorted tube, we're going to get the cells that we're interested in. We know we're going to lose some cells because occasionally we'll have a drop that contains cells that we don't want. But there are occasions when we want to use this, what we call enrich mode. And that is if I've got a cell that I want in a drop with a cell that I don't want, if that's a rare cell that I'm interested in, perhaps I'm prepared to accept a slightly lower purity because I'm going to get all the cells back that I'm interested in. And we can adjust the way that we do our sorting to accommodate that. And as I mentioned, single cell sorting is something that's really come to the fore recently. We've always been able to do it, but it seems to be that we're doing much more of it now. We're going to have a very stringent way of sorting because we really want to make sure that we have one cell of the type that we want. So we're only going to sort a cell when it's very well separated from any other cells in our sample. Now, in the BD system, I think this is sometimes a little bit confusing when you first start, so apologies if it's confusing. Hopefully we'll try and clarify it as we go along. Each of the drops that we make in our cells is divided into 32 virtual slices, if you like, and we're going to use those slices to define or discover where our cells are going to be, because obviously we know where our cell was at the interrogation point, and we hope we know where it's going to be when that drop is starting to form. And if we're lucky, our cell is going to be somewhere in the middle. Now, one of the things we mentioned in the last webinar is that we don't always know exactly where our cell is going to be. We think we know, but sometimes it travels a little bit faster, sometimes it travels a little bit slower. And that is heavily influenced by our sample preparation, which is why sample preparation for cell sorting is much more important than it is for analysis. But if my cell was dead in the middle of a drop, then even if it moved a little bit, I could sort that drop and I would sort the cell. But what would happen if my cell was somewhere near the leading edge of that drop? Now, there's the possibility that by the time it had reached the drop break-off, it may have moved. It may actually be in the drop before. Similarly, if it's towards the trailing edge, there's the possibility that it may move and not be in the drop that I'm interested in. So we have to take that into account when we set what we call sort masks in Diva. And the way Diva looks at this is in three ways. And the first way is to look at what they call a yield mask. And the way I explain this to people is we're looking at where the cell is within the drop that we expect it to be. And what we would do in this case, what I've set here is a yield mask of 16. So there should be 32 things here, but there aren't, for the sake of clarity. So if our cell falls within the middle of that drop, it's very unlikely to move too far so that it would appear in a different drop. So I'll just sort that cell, that drop. However, if my cell is likely to be towards the leading edge or the trailing edge, to make sure I capture it and therefore not to lose that cell, I'll sort the cell that I expect it to be in, but also this one, just in case. Okay, so I'll sort 2 drops rather than 1. Gives me more chance of actually sorting the cell that I'm interested in. The other mask we use is what we call a purity mask. And in this case, we're not looking at the drop where the cell is. we're looking at the preceding and the trailing drop. So again, I've set a purity mask of 16, but now we're looking at the bottom part of the trailing drop and the first part of the leading drop. So if my cell is here, that's fine. I can sort that drop. Similarly here, even though there's a non-target cell in the next drop, because that non-target cell is well away from the edge, I'm pretty sure that I can sort this drop without any contamination. This drop I would also sort because it contains 2 target cells, and that's fine. I'll get 2 cells for 1 drop. And I can also sort this one, although it's near the edge, because there's nothing in this drop. I don't risk any contamination. But remember, the order at which cells reach the interrogation point is a fairly random process, and occasionally I'm going to have a situation like this. I've got a target cell and a non-target cell in my drop. So clearly I'm not going to sort that because it runs the risk of me losing purity. But what about this situation? Actually, my target cell is in one drop, a non-target cell is in another, but it's quite close to the edge. I run the risk of that cell ending up in this droplet. So in this case, I won't sort that. So this is why we can lose cells that we want simply by the way that we set our sort modes. Similarly here, the cell is clearly in the drop, but I've got another cell in my trailing drop there that could potentially contaminate my sort. So I'm not going to sort this drop. And then the final is our single cell mode, or what we call a phase mode. And this time we're only going to sort the cell when it's in the middle, so in the middle of the droplet, not to the preceding or leading edge, and there's nothing either side of it. Here I'm not going to sort this drop because there's a chance I might sort an empty drop. Okay, that cell may have actually ended up in this drop when it reached the break-off point. Similarly with this one. Here I've got 2 cells in there. They're both cells that I want, but I'm not going to sort that drop because it's not single cell, is it? I'd be sorting 2 cells. Similarly here, although there's 1 cell in the drop, this one is another target cell, but it could potentially end up in my sorted drop. And again, I wouldn't be doing single cell analysis. So Diva software actually gives you a name rather than a set of numbers. But if you stop and think about it, maybe watch the video at a later date, what you can see is your yield mask always sorts 2 drops because it's looking at the preceding or it's looking at where the cell is in the drop. If it's in the first half of the drop, it's going to sort the cell in front. If it's in the second half of the drop, it's going to sort the drop behind as well. And what Kathy was showing us just now, the initial and fine tune with the Accudrop, the initial, we're always going to sort 2 drops, so we're not going to miss anything, which is why we're always going to get eventually 100% in our left-hand stream. When our fine tune, we only ever sort 1 drop, so it'll be close to 100, but it won't actually quite be 100. I mean, theoretically, the best you're going to get is about 97%, although obviously that depends on how well focused your camera is and how well aligned your Accudrop laser is. So we've aligned our machine and we've set our drop delay. We want to actually do a sort. We want to get some cells back. So today we're going to actually use some cells rather than beads that we used last time. And we're going to do just a 2-color experiment. We're going to use CD3, which we're going to label with APC size 7, and we're going to use CD4 labeled with FITC. And as Kathy's already told us, we're using the 70 micron nozzle for that because lymphocytes are quite small and the nozzle size should be sort of in proportion to the size of your cell. So 8 to 10 micron lymphocytes, 70 micron nozzle should be pretty good for that. So I will hand back to Kathy. We will go back to the ARIA. But there was a question there before we get to that.
Exactly. So yeah, the question is, does the checking the preceding and following drop make a purity sort longer than a yield sort?
And the answer to that is no, really, because the electronics are constantly looking at that stream of cells and they're working out where they're going to be in each of those drops. So electronically, this is all happening very, very quickly.
Right.
So there's no extra time involved in that, I would say. Well, maybe it's picoseconds, but
Exactly. No, you're right. The decisions are being made all the time, regardless of the sort mode, right? If it's purity, yield, or whatever. What makes a purity sort longer, if you want a certain number of cells at the end, is, well, the purity sort is going to be longer because there are more aborts, right? So if there are more aborts, the efficiency is lower, and so you need a longer time to sort the same number of cells than if you were doing a yield sort, right? But it's more because of that. But the decision itself is being made anyway.
Yeah, and these questions are always a balance with the question you're asking. You know, sometimes you can go quite quickly and have a high abort rate because you can get the number of cells you want quite quickly because you have a load to start with. But if you're looking for a rare population, you don't want to lose cells, then you have to think a little bit more carefully about the way you set the modes.
Exactly. Great. Yeah, Kathy, to you.
So back to you, Kathy.
Great, thank you. So I think everyone can probably see my screen now. And what I'd like to point out to everybody is I actually went ahead to kind of make sure that we were okay on time here. And I created an experiment under this OpenFlow folder in the browser. So as a refresher to everyone, to create a new experiment, you click on this new experiment icon in the browser. Alternatively, if you go to experiment and new experiment, what winds up happening is it will open up a copy of all of the templates that you have so that you can choose from one of those, okay? So what we're gonna do, now that I created this experiment and I renamed it, is I went ahead and I went to the cytometer settings. And in the cytometer settings, I chose the detectors that I wanted to use for this experiment. So we have FITC and we have APC size 7. So our FITC is our CD4 and our APC size 7 is CD3. And I made sure that our height and width were enabled for, in order for us to calculate or to gate on single cells and to be able to remove aggregates as we're sorting, okay? So all that I did was create the experiment, make sure that I selected the appropriate detectors and enabled height and width for forward and side. And then from there, I created a specimen to work from, okay? From the specimen, a tube is created. And this is similar to what we went over in our previous sessions for setting up an experiment in Diva. So what I'm going to do now is I'm going to go ahead and I'm going to load some unstained cells that we have so that I can start to get an idea of some of the gating that we want to work with, okay? And some of the generation of plots and gates, rather. So I'm going to click here and I'm going to call these our unstained cells. I'll leave the flow rate at a lower value to start off with. And I'm going to go ahead and I'm going to load from the acquisition dashboard. And then from the worksheet, what I'm going to do is I'm going to go ahead and get started by creating a dot plot. I click on that dot plot icon and I click and drag and I'll make it nice and big for everybody, including myself because my eyes are getting a little bit older. Okay. And it's taking a second for that to refresh. Okay. I'm going to left click and I'm going to do side scatter here. And what we can see to the right is that we have our forward scatter is off scale. And most of our cells are actually off scale. So what I'm going to do is I'm going to go to the cytometer window. And from the parameters tab, I'm going to reduce this forward scatter to bring our cells to scale. I'll start off with 250. And when I do that, I'll come in here and I'll restart. And we're starting to see our events come on scale. Okay. Now what I can do here, we're only running at about 200 events per second. I'm going to increase this flow rate to about 5 to increase the event rate here. And then I'm going to optimize this forward scatter. So I'm going to bring it down to 200 and restart. Our forward scatter and side scatter are now appropriate. And I can start setting up some of our gating. Okay. So what I'll do is I'll go ahead and start our gating. So each click is a node, and I select the polygon gate right up here. I'm going to right click and drill down. So from there, we'll be able to see only what's gated on P1. And then what I'll do is I'll change the x-axis to side scatter width. So it's side scatter width versus area. Select another polygon. Each click is a node. And we'll set a gate for our singlets. What we do in our facility is we do 2 single cell gates so that we can be as careful as possible to make sure that we don't have any aggregates that are making their way through. I always keep an eye on the volume to make sure I'm not running dry, because we want to make sure that we don't run any air through the system. Okay. So we have our second singlet gate here, and I'm going to drill down one more time. And then what I'm going to do is I'm going to look at our CD3 versus our FITC. I'm going to select on this plot and change it to by exponential. And what I see is I see my unstained population of cells right here. Okay. Now I do have some values for the fluorescent voltages that we've set up in our facility based on instrument characterization. So what I'm going to do is I'm going to go ahead and I'm going to put those values in right now because I have them here to the side. And again, this was based on a voltage characterization that we've carried out. Sorry, I meant to use 550 there in our facility. I'm not arbitrarily changing these values. Okay. So now what I'm going to do is I'm going to go ahead and I'm going to set my stopping gate so that we can start recording some of these unstained cells. So I'll set it at P3 10,000 and start to record. This way we have an unstained sample that we can work from to set some gates when we have our actual sample. Okay. Now, I did just mention very briefly that I set those fluorescent voltages based on an instrument characterization. If you go to our OpenFlow YouTube channel, what you will see is that we do have a video on how to optimize the voltages for your PMT detectors in Diva. So we highly encourage you to check that out. I'm going to go to next tube. I'm going to unload. And then what I'm going to do is I'm going to go ahead and I'm going to load my sort sample to make sure that everything's on scale. And to make sure that we can set our gates appropriately and see our populations appropriately so we can get started. So I vortex my sample. I'm going to rename this tube and we're going to call it sort sample. I have these a bit more concentrated, so I'm going to lower that flow rate here back down to about 2. There might be a question on how many events we can run for our threshold rate, like how many events per second we can run. You want to keep an eye on that frequency, right? So that number of droplets that are created every second is 88,900. And we could run typically at about 1/4 of that as far as our event rate goes. So a rough estimate, I can go to about 20,000 events per second with a 70 micron nozzle. I see all of my events here are on scale. What I'm going to do is I'm going to go ahead and I'm going to record this sample. Now, some people might look at this and say, this doesn't look that great. You have this population that's kind of showing up here right in the middle. That's because I started off with a very broad gate for scatter. Keep in mind that if I know that I want to sort the lymphocyte population and I'm confident in the scatter gating, I can hone in on this population and we can clean that up. Because keep in mind that your monocytes will stain for CD4, okay? And then if I do that, another important note here is that I will have a much smaller number of events that I've recorded based on our P3 gate. How can I check that? I can right-click on a plot and I can show the population hierarchy. And now what you see is I only have about 2,361 cells that have met the gating criteria of P1, P2, and P3. Okay, that's fine because what we're going to do is we're going to very quickly, we're going to carry out a sort. And what I can do is I can record the sample in addition to sorting at the same time. So I'm not going to waste time recording more sample when we can go ahead and sort and record at the same time. Now I want to go ahead and I want to sort out our CD3 single positives, and I want to sort out our CD3, CD4 double positive. So what I can do is I can go back to my unstained sample and I can set some rough gates based on where I think those populations might be, right? So it's P4 and P5 If I want to change this yellow color, I can double click on it and change the color right there. If I go back to sort sample, I can make any modifications I need to those gates. Okay, so what I'm going to do now that I know that I'm happy with where those gates are set, careful about my singlet gating, I'm going to check to make sure that my deflection percentages for these two, for the left and for the right, are appropriate, because we're going to do a two-way sort today. Okay, so what I have on the instrument is I have this collection apparatus that's specific for 5 mil tubes. Okay, now what I'm going to do is I'm going to make sure I put that on the instrument. And what you do first is you put in test tubes, right? These are tubes that are going to be, they were not going to wind up using for your actual sort, but you're using them just to check the deflection percentages, okay? And what you would do is you would turn the voltage on, okay? And then after you turn that voltage on, what you would do is you would turn the test sort on, and we see the deflected droplets from the left and the right. And then I would open up the door to the sorter and open up the door to the sorting chamber. And what we'd be able to see, if I open up this waste drawer right here, if I look in, I can actually see the streams being deposited. And we want to make sure that we align this left and this right so that it's making it into the tubes, okay? You don't want to go directly into the center, because you want to take into account the angling of the tubes and the deflection and the deflected droplets themselves. So you want to be very careful how you align that. This is a little bit different from the other instrument we went over last time, where it automatically set the deflections and we didn't have to change that. But here, again, just make sure that you check these values, turn the voltage on, test, sort, and then open up that waste drawer and physically confirm or visually confirm that it's making it into the tubes that you're looking to sort into. On this instrument, we can sort into 1.5, 5, 15. There's multiple different tubes that we can sort into, bullet tubes, in addition to multiple plate types. Okay, I did confirm this a bit earlier, so what I'm going to do is I'm going to turn that test sort and voltage off. I have my collection tubes on, and now what I'm going to do is I'm going to go ahead and I'm going to select on my global sheet that I'm working from, and I'm going to create a new sort layout, okay? The type of device I'm working from is a 4-way tube holder, and it's a 5 mil tube holder that can sort up to 4 populations simultaneously. For our purposes today, we're going to sort that P5. So if I left click here, I can add and sort P5 and P4. We'll leave our precision at 4-way purity. That's going to make sure that we get the purest sort that we can, because we're going to have a purity of 32 and it's going to have a yield in phase of 0. So that means it's going to sort 1 drop for every cell that we're going to sort. This actually becomes very important if volume is important to you. If you're sorting into trisol, for example, and you need to make sure that you have a very specific volume that you're sorting into, you have to be careful about that. Okay. Target events is how many events we're going to sort into that tube. If I put a value here, it will stop sorting once it meets that number of cells that were sorted. If I leave it as continuous, it will keep sorting and sorting and sorting until you tell it to stop. We can also go ahead and save our sort reports. So I'm going to select that we want to save all of them. And then for sake of time, we'll go ahead and get started. And what I'm going to also do is I'm going to make sure that I have more events recorded. Okay, so I'm going to change my stopping gate. I'm really interested in P5 and I want to make sure I have 10,000. Okay, you can change this number depending on your application. Okay, so let me go ahead. We're going to go ahead and we're going to start acquiring. I see my event rate is going at about 1,000 events per second, and I know based on what I just said about frequency, I can go a bit higher. So let me go to about 8. I'm going to change that value. And then what we're going to do is we're going to go ahead and start sorting. and select OK. When I select OK as I start sorting, what's going to wind up happening is we have our events that are being, we see our number of cells that are being sorted right here to the left and to the right. And we're also able to see the sort efficiency. Okay. It's a little bit hard to tell, but you can see as well the reflection as those droplets are being deflected. Increase that flow rate to 11 and go a little bit faster, because now we're going at about 4,500 events per second. And what you should see is if you have good eyes, is that to the left and to the right, we're getting that P4 and P5 population being sorted. So I'm going to continue on with this sort, and I'm going to let it go for a little while as we pop back to Derek. And then what I'm going to let it do is I'm going to let it go ahead and continue sorting for about another minute or two. And then I'm going to run some cleaning solution through the instruments that we can check to make sure our post-sort purity check looks as we expect it to. Because we want to be able to put this tube that we're collecting into for P4 and P5 back on to make sure that the results look as expected. So with that, I will go ahead and I'll also start recording a bit more and append to that file as I pass it back to Derek.
Okay. Sorry, go ahead, Rui.
Yeah, yeah. Just say we have a question here. It's actually related to Kathy when you were aligning the streams for deposition. So one of the questions here is, in your experience, how do you align the stream to deposit a droplet in each 384 well plate when doing single cell sorting? And do you always use, in this case, single cell sorting mode? And does the movement of the stage need adjusting between sorts?
That's a great question. So what we do is we try and make sure that we set it up so that we're deflecting as close as possible to zero while it still passes that, that waste catcher that we have, or the splash guard that you put in, right? So we try and go as close as possible to zero there. And then what we do is we set a custom plate up so that we can align for A1, and then I don't know the number for 384 off the top of my head. For 96 would be H12, right? So I don't have that number. And then what we do is we do a test sort where we sort probably about 10 or 20 drops for a 384 well plate onto a lid to make sure it's going into the center of those wells. What we also do is HRP testing, and you can find the protocol on our website to make sure that if you're sorting small volumes, it's making it into the center. It's a really wonderful protocol that you can use. It's been developed a couple of years ago. I forget who exactly developed it, but I think Rui and Derek probably know that and can chime in. And then what we do find is that, we keep an eye on the alignment of that ACDU to make sure it's not drifting over time. And we do have a laser and camera set up on our ACDU that we can track that in our facility.
Right, that's important. We have something that we call Well Tracker that we published at Saito in 2019, and we actually should have that on our website soon, where people can actually implement the same thing to track the ACDU, right, as the plate holder as it's moving along, to see if it's drifting. If it starts moving away from the well, we can detect that.
Okay. So I don't know how many cells we've got there, Kathy. Have we got enough to do a rerun in a second?
Yes, we do. So I can absolutely, we have about 60 and 50. So I can go ahead and get that started in just a second, Derek.
Okay, so what I'll do while Kathy is just cleaning the lines there, so we can rerun this. We'll just quickly go back. I realize, as usual, we're pushing our time limit. But what we're going to have to judge the success of any of our sorts, aren't we? And this is the slide we showed last time as well. And normally we're going to judge the success of our sort by looking at the purity, because we set a region around our CD4 positives, our CD3, CD4 positives in this, and that's what we should expect to get back. So we're going to rerun a small proportion from our sample, and hopefully they'll all fall in the gate. As we said last time, sometimes you'll get a few cells that maybe drift out of that gate, and we expect that because remember, each cell is not always going to give us exactly the same amount of fluorescence when it goes through the cytometer. So a cell that was just inside that gate where we sorted it, so it would be sorted, may actually give us a fluorescence that's slightly outside that gate when we rerun it. So, you know, quite often we're justified in just increasing that a little bit. But the important thing is you can see that it's one population, can't you? There's no single positives there. There are no negatives in there. And you know, this is what a new user would expect. I've got great purity. But what we want as well as a cell sorter operator is to know that if we've sorted 1 million cells into a tube, there are actually 1 million cells in the tube. So we also want to do a bit of cell counting, and we want to assess what we might call recovery. There's a little bit of controversy about what we mean by yield and recovery, but what I mean by recovery is what proportion of cells that I say are in the tube are actually in there. This is not something we're going to be able to assess today, but it's something that we should get into the habit of assessing with our sorts. And the way we would do that is take your tube, take a small aliquot, and take it to your favorite cell counter, whether it's an automated one or with a user hemocytometer, and count the number of cells, because we should be able to get 80 to 90% of the cells that we say we're going to into the tube. It won't be 100% because we're sorting electrostatically charged droplets. Sometimes they repel each other and sort of bounce out of the tube. Sometimes cells will hit the wall of the tube and die. But we shouldn't lose too many. So if we say we've got 1 million cells in our tube, it should be close to 1 million. The important thing about this counting is that you do it straight away. Now, occasionally I have people coming back and say, you know, I counted the cells, there was only 50% of them there. And then when you start asking them questions, actually they went for lunch, then they came back and they spanned them twice, they washed them, then they went for coffee, then they did the counting. Don't do that. Count them immediately. That's going to give you the best measure. The other thing we want to judge as well, and maybe we'll talk more about this in our next session in a month's time, is the yield. And I've sort of touched on yield already, and I go back to that GFP example. If I've got 10 million cells and 10% of them are GFP positive, I should be able to get 1 million cells back, right? But I can't. I can't for many reasons. Sometimes cells go through the laser too close together, so we don't know what they are, so we're going to not sort them. That's what we call a hardware abort. Sometimes my GFP cell is going to be in the same drop or very close to a non-target cell. So again, I would not sort those. So I won't get 100% of my cells back, but I should be able to get 60, 70, or even more back as well. And there are ways of assessing that, which are probably beyond the scope of today, but it's something that we can talk about. So that's a very quick run through of the 3 things that we want to look at if we want to assess a sort. So just for the last few minutes, we're going to go back to the ARIA. Hopefully I've given Kathy enough time to clean the machine.
All is good here, so it's good. We keep ourselves on our toes. So what I did here, thanks Derek, is I went ahead and I created a new tube and I ran a quick cleaning of the instrument. Because what I want to make sure is that we are confident that when we go to run our post-sort purity check, that we are ensuring that there's nothing remaining in the lines, okay? So that we can be confident in those post-sort purity results. So I'm putting on here our post-sort for CD3, and I'm keeping our flow rate at a higher value because I know when I put these on that we've gone ahead and we've diluted these samples quite a bit. So when I'm putting this post-sort on, what I'm checking for after I clean is to make sure that everything is falling into the expected range of where we want our cells to be. Okay, so I'm going to go ahead and I'm going to start recording. But what you immediately start seeing is that based on the cells that we have coming through, everything is looking really, really nice and as we expect, right? So like Derek mentioned, there might be, it's not going to be exactly the same potentially, but what we see here is we have this nice robust population that's showing up. And if you remember, we only sorted about 48,000 cells, and it was sorted into about 200 microliters of 1x PBS for the purpose of today, because this was done with these lyophilized PBMCs, so I don't really have to care so much about what I'm sorting them into. But if I go ahead and I create another gate here, and I capture these small outliers, what we see is it even goes up a little bit closer to about 99.8%. Should have changed that color, okay? So this is our one population that we sorted, which is our CD3 positive. And I think that should be sufficient for today. If we'd like to go ahead and check the other population, I would have to go ahead and do another cleaning since I'm technically running another sample through the instrument. But what we can see again is just that our purity is looking really on par with what we'd expect from the sort that we carried out today.
So we would expect the other population to be pretty similar. And as you said, we probably don't want to do that because we'd have to clean it. But that actually brings us to a question, Kathy, that we've had here from Adam. And what was the actual cleaning solution you ran there before the sort check?
So what I did for this purpose, I ran some rinse and then some water, so detergent and then water. Typically, we would run clean rinse and water because we would typically have viability dyes, nucleic acid viability dyes in our samples, and we want to make sure that we're removing that from the lines. I also like doing a sample line back flush as well for at least about 10 to 20 seconds in addition to that before I put the sample on.
Right. But it is an important thing to do, isn't it? Which is the corollary question there, because we want to make sure that the lines aren't contaminated with any of our unsorted sample, which could, of course, potentially contaminate our sort check.
Right. Just to add there, I mean, one of the things we noticed that if you use bleach, it may interfere with the post-sort purity check because, you know, as the cells are going through the line, if there are still some traces of bleach, depending on the fluorochrome, it might influence the, you know, you might lose signal because it just bleaches the fluorochrome. So that's one thing we started not doing, right? So just using water and detergent to clean the lines. There's another question here. So if sorted cells are very diluted, do we need to concentrate them? So for instance, spinning them down or remove liquid to count them? If yes, could this process affect viability?
So what I tell people, oh, sorry, go ahead, Derek. I'll let you go.
No, okay. I was going to say I wouldn't manipulate the cells in any way if I was wanting to count them, because, you know, spinning, you are going to lose cells. You could potentially, if they're fragile, you could decrease the viability as well. There are ways of counting reasonably dilute cells. Flow cytometers are very good at counting if you've got a volumetric flow cytometer, but I would try not to do any manipulation of that at all, because you do run the risk of losing cells.
Right, right, very important, yeah. You just take an aliquot, right, and count the cells, and that's it. Yeah. So the other question is, what do you sort the cells in if you want to culture the cells on, and that sort takes longer?
That's also a very loaded question. So it depends on the cell type and what you're looking to do, right? So if you're sorting cells that don't like to be alone, typically I recommend conditioned media so that the cells are nice and happy and they don't think that they're as alone as they are or as spread out as they are. Some cells like being sorted straight into some type of serum, right? So it all kind of depends. But sorting for culture, you might want to potentially sort at a lower pressure if the cells are happier with that, and that might take a little bit longer. But as far as sorting into different collection media types, that's not going to affect the length of the sort. If you're doing plate sorting and the population expression is rare or anything like that, those are type of things that will impact time. It's the frequency of the population you're looking to sort that will have an impact on the nozzle size.
Mm-hmm. I think with these sessions, we've really been looking at how the sorter gets set up to sort. Some of the issues around, you know, how we handle our samples, what we do with our cells afterwards, we might try and cover in the next session when we look more at sort of practicalities and troubleshooting.
Yeah, that's an important point, actually. That's actually one of the most important points in the success of a sorting experiment, right? Is how you handle the cells before, how you handle them during and after. So somebody was asking here, would you routinely clean between samples if sorting multiple samples? And the answer would be yes. Yes, absolutely.
Definitely.
Would increasing the flow rate, and so Kathy, I knew that this question would probably come because you did run it at 11. Would increasing the flow rate impact the sorting process as one is increasing the core diameter of the sheath stream?
So it theoretically shouldn't, impact the sorting process at all. There are things that you want to take into consideration, right? So if you're doing a sort per cell cycle, as you start increasing, your CVs might broaden a little bit, and you might have issues with that. So we try and keep that, event rate a little bit lower, and we try and keep the core stream as tight as possible. But when you're doing logarithmic and you're pulling out cells for a yes or a no, for antibody expression, expression of proteins, things like that, it's really not going to have much of an impact. Ideally, though, what you'd like to do is concentrate your samples that you can run at the lowest differential. But running it at 11 was not going to have an impact, as you can see here.
Right.
Today.
It'll have an impact on the resolution of the data, but it's not going
Right.
to really affect
the
sorting process itself.
Exactly. The resolution is very important. Yeah. So actually, I usually recommend for the ARIA not to go above half of the maximum flow rate if you don't want to impact resolution.
Yeah.
But if you have things that are well separated, then it's not a big deal.
Yeah.
The only thing
Again,
I would add,
you're in control, right?
Exactly. The only thing I would add there is that when you're checking purity, it's important to use the same flow rate to record the purity check that you used for the sample when you recorded it originally, just to compare apples and apples, right? So if you run the sample at 1, you record it at 1, and then you record the post purity check at 11, you might see differences there just because of the resolution, right? The loss of resolution. So I think that's an important issue. And then finally, we have a question here. What would be the maximal time you sort the sample if it is going further for sequencing?
It's a very good question, and I'm not entirely sure I know the answer to it.
Yeah.
I would say nobody really knows, because as we were discussing, we don't really know the impact that it's having on the cells. We know that it may have an impact on some cells, but so the way to assess this would be usually the genomic cores will have some kind of quality assessment, typically viability, and so you can be monitoring the viability of your sorted product as time is going by. If you see that it goes below that quality control, then that's it. Your time is out.
And I would also say that you need to have a lot more contact with the genomics facility than maybe we used to have. So knowing the outcome of the sort is very important for us to know, because if something's wrong, we can do something about it, unless we know it hasn't performed as we like.
Right.
Or conversely, let us know if it has. That's a good thing to know.
Exactly.
And also, if there's any possibility for it, staggering sample prep to minimize the samples from sitting out for too long is something I would suggest as well, right? So if you have 10 hours of sorting you're looking to do, if there's any way that you can kind of stagger that process, that might be beneficial as well, so they're not sitting out as long.
Mm-hmm. We have here another question. This is more also for logistics in terms of the operations. Somebody's asking how many appointments per instrument are given in a day in your respective facilities. So
a lot.
Let's say, let me do the math quickly. So 400 divided by 22. So in 22 days, we typically do 400 appointments, and then we would have to divide it by the 4 sorters that we use as assisted. Then we have an extra 200 sorts for, between another 2 sorters. So let's say 100, 22.
Yeah, I suppose
it would be 5.
Well, he does that maths in his head. Yeah, it could be 1. Sometimes we are sorting all day long, and it could be maybe 6 or 7. I mean, what we would say is we always leave half an hour between sort bookings. So one that we can potentially clean the machines, and sometimes we need to change a nozzle, change filters and so on. So, you could have a day where we did 5-hour-long sorts back to back.
Right.
But in reality, it tends to be 1 or 2 per day, I think, per machine.
Mm-hmm. Right. So another question here is for the cleaning between samples. How long do you run the clean, rinse, and water for?
Between samples, we typically tend to run at a flow rate of 11 and do about 30 seconds to a minute each. Is what I tend to do.
Yeah, the best way is to look at the number of events that are showing up. If you see that it's 0, after 30 seconds or something, right, then probably it's okay. If you're still seeing a lot of the events that you were seeing before in your original sample, then maybe you should clean it a bit more, a bit longer.
Yeah, it depends what you're seeing, doesn't it? Yeah, if you see a lot of lymphocytes there, yeah, if you've got a little bit of stuff in the corner, maybe that's not so much of a problem.
Yeah. And you want to make sure your cleaning reagents are clean,
Okay.
right? So you don't want your water to be sitting out
fresh each time, I would say.
Exactly.
Yeah.
Exactly.
Fresh cleaning reagents every time you do it.
Yeah.
Okay.
Okay.
Shall I go back to my screen for a second for the last couple of slides? So yeah, obviously a chance to ask any other questions. That's great. We've had quite a lot of questions, which is brilliant. And if you think of anything later on, please do reach out to us. So we will be sending out a questionnaire after this, hopefully. So please take a couple of minutes to fill that in. And the question right at the beginning is this being recorded? Yes, it is. And we will put that onto the OpenFlow cytometry channel on YouTube sometime next week. So if you search OpenFlow cytometry, you'll find that easily enough. And all of the things that we've done are on there. So, subscribe to the channel, like the videos. That'll help everybody. So even though Kathy is moving on to pastures new and better, don't tell Rui I said that. But we will be running another session next month on the 14th of April, if I got the right date, or was it the 16th?
Oh,
it's Friday.
16th, yes.
Yeah. 16th. Yeah.
Yeah. Okay. So, ignore that. But if you go to the Crick What's On site where you can register for that, that will give you the right details. And we're going to do another session on sorting, where we're going to look at maybe at some of the things that we've talked about that are maybe a little bit more peripheral, because as Rui said, what we do to our cells before they come to the sorter and what we do with them afterwards is just as important as the sort itself. So come armed with questions. We're not quite sure how we're going to run that one yet, but that's the sort of thing we will cover.
Exactly. Just one final question that came up. If we routinely exclude platelets, yeah, we can answer it in the third session. But Adam, just very quickly, you typically would exclude them with a threshold if you want to exclude them from simply from the analysis. But if you want to exclude them from sorting, like if they are contaminants, then you actually have to include them. I think we addressed that a little bit last time, right? The threshold, the importance of thresholding.
It's the threshold. Everything below the threshold is invisible to the machine, so it will be sorted along with your cells.
But yeah, but we can address that later.
Just the final slide there is our email addresses. Obviously, Kathy's will change imminently, but you can also reach us through the Gmail address there, the OpenFlow Cytometry Gmail address. And of course, you can follow us on Twitter. So, as usual, we've managed to slightly overrun. Thanks to everybody who stayed with us.
Thank you very much.
And we will see you all in a month's time. So take care, everybody.
Take care. Bye-bye, everyone.
Everybody.
We'll see you soon.
See you soon.
Bye.